wonderful people. My name is Teun Dekker. I will be your pro-rector today, representing the authority of the rector of this university, under whose authority the doctorate will hopefully be conferred in a little bit over an hour. And I would like to welcome you to this defense. What you are going to see is an official academic ceremony with rites and traditions and customs and opposition, but we should never forget that it is first and foremost a celebration of science and a celebration of an awful lot of work that has been completed. These booklets, they seem so small. There's hundreds of them over there, and we should never forget how much work and sheer willpower it takes to make these things happen. And this is something to be celebrated at a festive occasion like this, and so I hope that we can keep that in mind and enjoy the show. Hereby, I open this academic ceremony in which Viola Spagnuolo will defend the academic thesis entitled Mirror, Mirror on the Wall, Pushing the Boundaries of Gravitational Wave Detection. Dear candidate, may I invite you to present a summary of your study and the conclusions of your thesis.
Hello everyone. This is the title, the topic of my thesis. During this year in Maastricht, I explored some material properties for the mirrors of gravitational wave detector. And to better understand how the importance of these mirrors, we have to look at the design of this mirror, this detector. Sorry. Here on the left, we have a diagram which shows basically the idea behind the gravitational wave detector. Our goal is to measure the minute change in distance between the mirrors on both arms of the gravitational wave detector. On the right, so you can see we have the red line, which is the coating thermal noise, and is currently a dominating noise source for the gravitational wave detector. How the mirrors look like. Here on the left, you can see we have a microscopic point of view for this mirror. On the right, you can see we have a nanostructure for the mirrors of gravitational wave detector. We usually have a highly reflective index stack made of two materials. The part in blue is the high refractive index layer, which for the current detector is a mixture of titania and tantala. And the part in pink is the low refractive index material, which is silica. Fused silica, and all of this multi-layer structure is deposited on fused silica substrate. For the current detector, to reduce the thermal noise, we are looking at some new material to replace the part which presents the highest mechanical loss, which is in particular titanium and tantala, and mainly the tantala. For most of my research, I looked into a single layer of high refractive index material. But what are the quantities which that play a significant role into the coating thermal noise? Here you can see we have an expression, the equation for the coating thermal noise. We have the coating thickness, the mirror temperature, the beam radius, and in red the coating mechanical loss, and in yellow the elastic properties, basically the Young modules for the coating and the substrate. These are the two main properties I work on during my PhD. So let's start with the setup and method to measure the mechanical loss. This was my first setup when I started at the end of 2019, and there was no lab at Maastricht University, but just an office room. This is my daily work for 3 years, and this is the evolution of a GENSE setup up to the end of my PhD. On the left, you can see we have a final setup, a final configuration for the setup, and we have all the devices connected to the vacuum tank. What we have in the vacuum tank we have the GENS, Gentle Nodal Suspension System. This system is basically how we can balance the sample on the spherical support made by a silicon lens. And in that way, we can avoid any kind of frictional force damping at the contact point between the two surfaces, the sample and the disk. In that way, the only applied force to the sample is the weight of the sample, and for that reason, we named basically Gentle Nodal Suspension System. Really close to the sample, we have an electrostatic actuator to excite the resonance frequency of the sample using the ring-down method. What is the mechanical loss? Mechanical loss is a material property inversely proportional to the object quality factor. We measure the mechanical loss exciting the resonance frequency of the sample, then we remove the excitation, and then we are able to track the amplitude decay or the relaxation time of the sample using the ring-down method. This relaxation time is proportional to the quality factor of the object, of the sample we want to measure. The higher is the quality factor, the slowest is the ring down. The ring down, in fact, we can take from a few seconds up to several hours. In the plot here on the left, you can see an example of rather fast ring down. What are the steps to measure the mechanical loss? You have to consider that we have a sample composed by two parts, the substrate and the coating. First of all, we need to characterize the substrate, so we measure the loss, the uncoated loss. Then, after the coating deposition, we measure the coated loss, substrate plus coating. And in this case, the loss arises from both the silica substrate and the coating. To get the final results about the coating mechanical loss, we use this expression, where we have the energy ratio, which is something we get from finite element analysis, and is the ratio between the elastic strain energy stored in the substrate and the elastic strain energy stored in the coating. This quantity is multiplied by the difference between the measured coated loss, substrate plus coating, minus measured uncoated loss. Let's start then with the material I explored during my PhD. I started with some silica titanium mixture because, as I said before, for the next upgrade of current detector at room temperature, the idea is to find a new material to replace the titania and tantalum, in particular tantalum. The collaboration moved into the range of already known material, like silica and titania. And, for example, for titania, titania presents too high crystallization temperature, and this is the reason why we mix into the titania into the silica to get the best performance from, for example, high refractive index from titania, the lower mechanical loss from silica, together with the highest crystallization temperature through the silica. This work started elsewhere in GW collaboration, and I have continued this research line during my PhD. I investigated some sample of different silica titania concentration in single layer configuration to understand the material itself, and in multi-layer configuration to look at the performance into the stack. In the plot here on the right, you can see how the loss, mechanical loss, behaves as a function of heat treatment temperature. The loss reduces with increasing heat treatment temperature up to a certain point. At this point, we have an increasing again of the mechanical loss due to some damage, crack, bubbles on the top surface of the sample caused by the heat treatment. My work focused basically on finding the best concentration and the best temperature that minimize the mechanical loss. And we got as a result a factor of 2 lower in terms of mechanical loss than the current coating. My sample were investigated for direct coating thermal noise measurement at MIT, and this results in a PRL publication where the first authorship was split between a PhD student from Glasgow, MIT, and me. This is the most important results from my PhD, and really important results also for a GW collaboration. While silica titania represents a new material for the current detector at room temperature, the amorphous silicon, which is another topic from my thesis, is a material for future detector as Einstein telescope. For the reason why this material presents lower mechanical loss at low temperature. Usually when we measure the mechanical loss, we measure the mechanical loss at different resonance frequency as a function of annealing heat treatment temperature. And here you can see how the reduction in terms of mechanical loss through the heat treatment step, starting from the AD, which is as a deposited state, right after the coating deposition, then 300 and 500 degrees. These are other topics explored from my PhD. They are highlighted here in the plot on the left in the context of current research field from the community. I did some loss consistency investigation across substrate from the same batch production, basically to understand if we can get a uniform loss level for substrate sample in general from the same, produced from the same company at the same time from the same device. Titanium germania sample, another topic from my PhD. I investigated the heat treatment's effect on this kind of, on the mechanical loss in particular, and on the microstructure, because as I said before, the heat treatment can create some defects, bubble, cracking on the top surface of the sample in general. Then new sample geometry as rod with the new high index glasses to determine basically the influence, the impact of the geometry on the mechanical loss and resonance frequency. Here there's a brief summary about the topic during my PhD, and I take this chance to say thank you for being here, and thank you for the support during this year.
Dear candidate, thank you very much for your presentation. The opposition will now be opened by Professor Dr. Marcel Merck, Professor of Particle Physics at Maastricht University, who is also the chair of the assessment committee.
Thank you, Mr. Chairman. Dear candidate, first of all, my congratulations with the manuscript. I'm an outsider on the topic, but I read it and I really enjoyed your presentation style, presenting all the details of your work, and in particular also the many diagrams that you had that really helped me to understand what was going on in all the cases. So my compliments for the manuscript. Then, as far as questions go, my first question is a very naive one. I'm reading the work, and then I say, okay, about these mirrors, I never thought in detail how this all works. Why don't you just use a metallic mirror rather than this Bragg reflection mirror system? Can you give me a simple answer to why you would do that?
Thank you for your question. Can you say again what is the main topic of your question?
So, I mean, if I understand very well, you use the Bragg reflection mechanism of this coating in the mirror, and that's all your work is based on that. But if I just look at the mirror at my home, it doesn't have all that. It just is a metallic, simple mirror. Why not just put that one in?
Mm-hmm. Yeah. Thank you. We use basically the idea behind the mirror is the main goal for these mirrors is to get the highest reflectivity. For that reason, we use the Bragg reflection, because in that way we are able to reach the maximum reflectivity from that mirror.
Okay.
As I said before, we have a different we have a nanostructure, a multi-layer structure in these mirrors. So we have an alternative layer of high refractive index material and low refractive index material. This is done to increase the contrast between these two materials, then to increase the reflectivity inside within the mirror. Here in my thesis at page 29, I have some instruction about how we perform, what are the optical indication for this mirror. In particular, we have that, for example, the optical thickness of the layer are really important, because we have the physical thickness of the sample, the material we are looking at, and then we have the refractive index. This created the multiplication between these two parameters, create the optical thickness, and we know that for this mirror we look at a reflectivity of about lambda over 4 to get the maximum in reflectivity. Why we want maximum reflectivity? Because we have a laser beam within the detector. We are looking at high in terms of this material.
No, I understand. I think you've answered in much more detail than my question was, so thank you very much for that. Maybe I come back later to the mirror, but I would like to have time to one specific thing that intrigued me very much, and that is on page 26, 27 of your thesis, and it's on the suspension thermal noise. And what I see there, I had to read very carefully this first paragraph on page 27 a few times, and then finally I think I understood that you have, when you have a vertical mounting system, you have some vibrations there, and that then translates into horizontal movement. Not really horizontal, because the Earth is not flat and the laser makes a little bit of an angle. I decided, let me calculate that. And I get the value of 1.6 millirad over 10 kilometers, yeah. Einstein telescope. If you agree to that, it's fine, otherwise correct me. And then I was wondering, is that an important effect? Also, since this thing in this cavity reflects about 300 times or so, does that really make a large contribution to the noise? So there's 1.6 per mil component?
Yes, thank you for the question. Yes, this is really important, because the suspension is the main part of the detector for gravitational wave detector, and in particular because for the suspension we have a lot of vibration which are can be added between them into this system. In particular, the horizontal one, because you have a transmission basically of all the vibration through the suspension up to the mirror. For that reason, also basically the investigation about the thermal noise is something also interested by for the suspension, because we have the fiber, fused silica, different kind of material, and this material also in terms of the geometry of this system creates, they present, for example, other kind of fluctuation, like I said here, the vertical thermal fluctuation, the violin modes, which can increase the vibration in all the system, and they can be transferred to the mirrors.
So indeed, it's an important source, and Einstein telescope is 10 kilometers long, and then I thought, hey, in the US they're going for this Cosmic Explorer, which is 4 times as long, if I'm correct. Mm-hmm. Do they have, is that bad news for them? The effect is at least 4 times as big, I would think?
Yes, I think so. We have...
But they should worry, that's what you say.
Yeah, sorry?
They should worry.
Yeah, they should worry. Everything.
Okay. Mr. Chairman, if I may continue another question. Let me then come back to the mirror and the system with the Bragg reflector, and then I was looking at page 30, how this worked, and you explained already the principle behind it. And I was wondering, is this, because a mirror, if I'm correct, when you stand in front of a mirror, left goes to right, right goes to left. So I think light makes 180 degrees phase shift. I think the phase of the wavefront. But is that perfect? So if you make such a mirror, is that 180 degrees phase shift perfect? Also given the fact that you reflect 300 times in this Fabry-Quérot cavity, is that a source, also a source of noise? That maybe this 180 degree is not perfect? Or can you tune that? Or is there anything there that I missed?
Yes, anyway, in the system we have some amplification of the vibration, and
because I'm asking myself, suppose these various photons get a different light, phase shift or so. Does that gives you because you're measuring the phase shift in the interferometer in the end, at the phase of the wave function. Is there anything there at this mechanism of not having exactly, what is it, a quarter lambda or not, or I have no idea. Is there a source for noise just purely on the Bragg reflection mechanism? Or is it just my imagination, which is well possible, by the way?
Yeah, basically, what we can say that these photons create some problem on the face, on the surface of these mirrors. We have, for example, shot noise. We have other kinds of noise source. And what we do is basically to find, increase, for example, the laser beam on the top of the surface for this mirror to reduce this kind of additional noise source on the mirror. This is something that...
I'm not sure I follow 100%, but I was wondering, is it correct that I say that the phase of the reflected wave makes 180 degrees phase shift? Is that okay? And is it possible that with these Bragg systems, with this multi-layer system, that you can actually play with that, or can you make that different? I think I read that somewhere, but I'm not 100% sure. And I was wondering, if that is the case, do you have to be very careful how you tune these layers to get that phase correctly reflected?
Yeah, but basically what we do is, for that reason, we are looking at lambda over 4 design for this mirror, because lambda basically is the wavelength of the laser that we use, and we look at lambda over 4. In that way we have the maximum reflectivity, so we don't have any kind of problem for additional phase into the system.
Okay, thank you very much.
Thank you.
I think I return the word to the chair, and thank you for the discussion.
Thank you so much. The opposition will now be continued by Professor Dr. Andreas Freyser of the Free University of Amsterdam, where he is Professor of Gravitational Wave Research.
Thank you. Yeah, dear candidate, also for me, congratulations on finishing this huge amount of work. It was a pleasure to read it. I especially enjoyed the high quality of both your textual and the diagram presentation, so that is really probably a mirror of the high quality of the work that you've done, but it was because of that a joy to read. Yeah, I also have some interesting scientific discussions prepared for you. I would like to start with chapter 6. They describe an experimental setup that you worked on, but I was intrigued because before you described the technique that I also knew about the disks on balancing on this, but here you're using rods, and that I had not seen. So can you explain to me why you're using rods in this particular experiment?
Thank you for your question. Yes, this investigation is a bit different from all the measurement which I did during my thesis, and I know that the geometry is completely different. But in this case, first of all, we had this material, which are material really close to the silica properties, and the vendor gave us this material on a rod shape. Okay. So something when we want to investigate some kind of material, we have also look at what the vendor can provide for you. But anyway, we found an interesting topic because The mechanical losses in general are material properties, so no problem about the geometry. So our goal basically is to look at the material itself, and you can play with this material also using a different geometry. In this case, this was really interesting because with a completely different geometry, we have the chance to look at different dissipation mechanism into the system. For my investigation, mechanical loss is the main one, but with this kind of geometry, I look at the thermoelastic noise. And the thermoelastic noise is something which arises from some deformation and diffusion of the heat inside the material. This obviously creates some problem for our measurement and in a microscopic point of view, and in microscopic point of view for the detector. And the main aspect of this investigation was that using a different geometry, so playing with, for example, length of the system, you can put away, for example, the thermoelastic loss away from the range of your measurement. If you look at the picture 6.1 at page 146, we have a nice graph where you can see you have the thermoelastic loss, the thermoelastic peak, and if you use different lengths, for example, starting from 1 millimeter up to 200 millimeter, in particular 200 millimeter is exactly what we have for the rods, because I measure 2 rods, 167, 65 millimeter and 200 millimeter. In this occasion, basically, you see that you can see that the thermoelastic loss is completely out from your measurement frequency range, which is on the right, because usually when we measure the mechanical loss, we are in the range of 2.5 up to 30 kilohertz.
Yeah, thank you. That brings me to my second question on this, because as you said, it's a principle, it's a material property that you're measuring. But here I also see that it depends on the geometry. So here you're measuring a bulk rod, but you're thinking about coating, where the material shape is very different. So you have very nice measurements. Can you use those measurements to predict the performance of a coating with this material?
More or less, yes. But for example, this is a particular material because it's at the beginnings we knew that this material was similar to the silica because of the idea for the new investigation for the mirrors of gravitational wave detector. For the reason why we know that silica is the best material we know, the scientists are basically us. We are looking at material with the same properties of silica, but silica presents the problem with the low refractive index. So the vendor provide us this material, which is quite similar to the silica, but after the measurement, we saw that basically there are a few % of silica. Because the doping, the mixture of the silica properties with some metals can increase the refractive index of that material. But basically, this is yes for the coating, but with not the optical properties of the coating. It's just to understand if it is something that we can use in future or not.
Okay, thank you. Yeah, I think that was very interesting for chapter 6. I would like to move, staying more or less on the measurement, but now to chapter 4, because there you also present measured values, and you compare them also to theoretical values, and there's quite a difference. But I couldn't quite understand how much that impacts the loss, because you give me the values just for the elastic numbers. So how much difference do I get in loss comparing when you compare your measured value to if you would have used a literature value? How much difference would it make for a coating loss?
Thank you for your question. You mean in terms of substrate encoding?
Yeah, when you so you measure in here particular Young's modulus variations between 100 gigapascal and 150, but how much does that change a coating if I now make a coating with that material?
Yes, okay. Yeah, as I said during my presentation, to get the final results about the coating mechanical loss, we use an equation where we have the elastic strain energy, which is at page... Sorry, a moment. One moment. Okay. Equation 3.21, page 95. So to get the coating mechanical loss, we use basically, 3.20, the equation is duration between the elastic strain energy of the substrate divided by the elastic strain energy of the coating. To get this elastic strain energy is something which is stored inside the substrate and the coating after our excitation. And when you have, for example, a driving force applied to your system. And if you look at the equation 3.21, we have the expression for this relation, which is proportional to the Young modules of the substrate and the coating. This means that basically, for example, during my investigation also for the rods, if you have not the right Young modules, elastic parameter in general, you can have an underestimation or overestimation of your system. And this means obviously is directly proportional to the mechanical loss. So for well-known material, we have, like for example, silica, we have a large literature about the elastic property, but sometimes it's also really useful to have the experimental value, experimental data about this elastic property, which is something we can do for doing some comparison between the data, the simulation, because finite element analysis is really helpful tools for our study.
If I have time for one more short follow-up question, then so why don't you always just measure the Young's modulus if it's so much important that you use it? So what is the difficulty?
More or less we can measure because we can extrapolate the Young modules from the measurement. So, and
for all materials?
For all, yeah, almost. Because if you have a mechanical loss measurement and you characterize the sample, because there are, in few steps, we have a full characterization of the substrate before the measurement, so we know the geometry of the system. And for example, in the simulation, we put data like the diameter, all the information that we have on the geometry. And in that way, you can get the simulation. Then you have the measurement. So basically, making comparison between the measurement and the simulation, you can arrange to get a final result which is consistent between the two, and you can extrapolate the Young modules.
Yeah, okay, thank you very much.
Thank you. The opposition will now be continued by Professor Alessandro Bertolini, Professor of Gravitational Wave Detection Technologies at Maastricht University.
Yeah, dear candidate, can do more than joining the compliments of my colleagues. So your thesis is very well written, is very clear in the explanation of the concepts and very rich in details about the experimental activities. Also the analysis is very clear, so it was really nice to go through all the plots and understand all the steps that are involved in this very intensive, very intensive research. So, however, I would like to ask you a few questions about some aspects that piqued my curiosity. So, the first one is page 123. there is this plot that is about the study that you made about the quality, say, of the substrates. And in equation 4.2, you use a specific function to fit the results. Can you briefly explain what is the physics behind the function that you have chosen in this fit?
Thank you for your question. Yes, because in this case, when I did these measurements about titanium germania coating, what I did is basically, in this case, we got from the vendor the sample ready coated. In that way, we cannot measure the substrate before. So we did some analysis because we got the substrate. I had the substrate from the same batch production, so I can extrapolate the mechanical loss for this substrate. But what happened in this case that from 4 substrate, as you can see here in plot 4.6, we had a quite similar mechanical loss for 3 of them. Instead, another one presents a higher mechanical loss. And I did some investigation about, for example, the age effect. This is basically what we call the age effect, because the age effect is something that happened to the substrate due to probably some not really good polishing of the substrate of the sample that we want to measure. And what's happened that we have, for example, the entry points for this substrate through the edge, the barrel of the system. The entry points of dust, moisture, all these component can create some degradation of the sample through the time. This is the general idea about the edge effect, and in this case I used this formula to separate basically from the main part, the central part of my substrate and the edge. In this plot number 4.7, what you can see is that basically I consider the average mechanical loss from 4 discs and the red one, and from 3 discs the blue one, and I did the fit to this data considering just the central part of the mechanical loss, excluding completely the age effect of the system. And you can see from the 2 fit that basically the difference is quite small. So we know that basically from our sample we have obviously an edge effect, and for that reason we can make some conclusion about if we want to use 3 or 4 of this substrate to get an average mechanical loss for in this case for titanium germania.
Okay, thanks for the clarification. And about the frequency-dependent part, where is this dependency that you use for the fit coming from?
For example, for most of my sample, we didn't get any frequency dependence, because the frequency dependence is something that is related to the material, to the temperature for the sample. Usually for my sample, I didn't consider the frequency dependent, but this formula comes from the coating collaboration of all the group. They can consider, for example, if you look at the final plot here 4.10, you see that for my sample you have just 1 point, which is the average mechanical loss through all the resonance frequency. Instead, for example, for material from the current research line, you have some line which is presents some inclination. This is basically the case where you have a frequency dependent for some sample, which is a characteristic of the material, the temperature, and.
Okay. Yeah. Thank you. I would like to stay on chapter 4. So about the method that you've used to extract the Young modulus from the frequency shift measurements. So as my colleague said, why you don't do it often, because it seems a very good strategy to reduce systematic errors in this measurement. So my question is, how would you rank the systematic errors in the measurement that you have done, starting from the worst offender, so to say, to the accuracy of your measurement? So what is this, the main cause of systematic errors in the measurement that you do, and how that could be improved?
Thank you. Thanks for the question. Yes, for the Young modules, what I can say is that basically, as I said before, sometimes we have a literature about the Young models, but this literature depends on also about the deposition system. For example, for the amorphous silico, in this case, we have a different kind of deposition technique. For that reason, it's important to get an experimental result about the Young modules from each of these systems. We are quite confident for material like fused silica about the literature data. We usually have this kind of exploration when we have new material, when we know for instance, amorphous silico is one of this main topic because the amorphous silico has quite higher difference, quite difference between the deposition technique, so we can compare our data with other data from a completely different system of the deposition technique. So the change in our measurement about this is here I have presented a macroscopic difference between the literature and the data, and in particular the evolution through the heat treatment step. But usually we are quite confident on the results on material that we know. Is it something that is right?
Yes, if I may ask last part of this question. So, but then you trust the literal value also between the post-deposition heat treatment and another one? Because the data in table 4.1, they show that there might be quite an evolution in the, say, stiffness of the material during the different steps. So there is clearly a change in the structure of the coating. So when, while I think in the other measurement that you presented, you used a single value for independently on the heat treatment steps you are looking at. So is this a limitation, or you do care only to the last value that showing the highest quality factor?
This can be a problem. Mm-hmm. But we do this kind of exploration for the elastic properties in general. So it's something which is behind the characterization of the sample, also through the measurement.
Okay,
so,
thank you. Thank you very much.
Thank you. The opposition will now be continued by Dr. Kerry Vos, Associate Professor in Theoretical Flavor Physics at Maastricht University.
Now, thank you. Dear candidate, let me also join my colleagues in first congratulating you on finalizing this work. It's very nice, and also for all the work you have done, which I think is still very nicely summarized here behind you. What I also liked a lot from your presentation is seeing this before and after pictures of the setup, which I think shows a nice summary of all the work you have done here. So that's very nice. You have done a lot, so I also have some questions, because sometimes I was a little bit confused. And the first question I have, so I was looking at your statements, and then my eye was caught by one specific word. So I would like to ask one of your parents maybe to read statement 4, to the audience as well?
Lorentzian kits provide more accurate determination of height mechanical losses compared to ring-down methods.
Thank you. Thank you very much. So I saw the statement and I started looking in your thesis. I think I traced down the origin of this statement to your section 6.4, where you discussed this a little bit. But when I was reading this, I was maybe a little bit confused, and also by the results that you got versus like how strongly this statement is put here. So maybe you could explain your findings first to me.
Yes, thank you for your question. We have two ways how we can measure the mechanical loss in general for the system. For the system with the highest quality factor, we usually use the ring down. But for example, for the reason why during my investigation about roads, I have not quite high quality factor. What I did, basically, what I had during this measurement, that the ring down in this case was really fast. If you look at the picture, the figure 6.7 and 6.8, you have two different cases. The ones for resonance frequency at 9 kHz, where you have a slow decay, but with a lot, because slow decay means basically high quality factor, but with a lot of data point. Instead, in the case of 6.8, you have a few data points. So in this case, it's impossible to get, it's not quite accurate your measurement to get the final mechanical loss of your system. For that reason, you can use, alternatively to the ring down method, the Lorentzian fit. It's a quite a different system, because for the ring down, basically you have a system, you have a driving force on your system, then you remove the excitation and you have a freely decay of your system. Instead, for the Lorentzian, basically we have an excitation through the electrostatic actuator on your system. Instead, for the Lorentzian fit, we use the excitation, the driven force on your system. In this case, for the ring down, what we measure is the relaxation time. With the Lorentzian, we have basically the frequency response of your system in the region really close to the resonance frequency. Instead, for the ring down, we have exactly the resonance frequency of your system. In some cases, obviously, for 90% of the time, we use a ring down because it's a more easy way. We are more confident, not more confident, we are confident in the results. And, but for this, in this case, I did a comparison between the results from ring down and Lorentzian fit, and in particular for the case where you have few data points, you have the problem of the signal to noise ratio, because for example also for higher frequency resonance you have a higher noise from, for example, the instrumentation, so basically your signal disappears before the end of a relaxation into the noise from the measurement. So you are not quite confident in these results. For that reason, when we have this kind of material with loss which are not particularly low, you can use a Lorentzian fit, the Lorentzian fit, and you are quite confident on the results, because you know that the Lorentzian is related, proportionally related also to the mechanical loss of your system.
Okay, yeah, so because maybe a part of the, or what I wanted to know indeed is if you now know beforehand which one you have to do, or if you're always going to do both, which is a bit the idea that I got here. So that was maybe part of my question
usually
as well.
For all my measurement, I use the ring down, because we know that for this kind of material with this quality factor, we can use the ring down. And during the measurement for the rods, I have seen that we have a problem.
It doesn't work.
In terms of few data points, we are not quite sure about this data, so we can use also this other kind of method to have the results about the mechanical
Okay, and then maybe just finally to understand for me, so I see also some numbers in this section. So indeed, for figure 6.8, you did it in both cases. And then the values that you get also differ a bit. But how significant is this difference that I see here? So I see, I don't know, a phi of 1.9 with one method and 2.5 with the other, times 10 minus 4. So is this an important effect? Can you give me an idea of that size?
Yes, obviously you are underestimated or overestimated your mechanical loss, which is the final results you want from your sample. So if you know that you have a more confident way to get that results, and is something that we use always through the measurement, is better in this case to use this kind of method.
So I think where I'm aiming at a little bit is I was wondering if these values are so important, why there's not a plus minus or an uncertainty associated to them. And what we sometimes also do, very different field, is then if you have two different methods, you use somehow the difference between the two as an additional uncertainty. So that's why I was wondering, yeah, how important is that change here?
Sorry, one moment. I don't quite understand you.
No, it's more of a comment there, indeed.
Okay.
Yeah. Okay. So my next question was actually about. Well, we can go to figure 6.10, which is on page 164, if I may, by the way. Yes.
6 point.
Figure 6.10.
Yes.
So this is the figure you also showed in your presentation, and this one actually came back quite a few times, and then you added basically your results to it. So this I liked a lot. But I was still wondering a little bit, what would you say are the main takeaways from this plot? Or do you agree with me that this basically summarizes a little bit your results? And maybe you could also tell me why now this demonstration of this lack of frequency dependence is something that you're very happy with, or that's something that you would like to see.
So in this plot, as you said, thank you for your question, we have a recap about my measurement in the context of the research line from the coating group for gravitational wave detector. The frequency dependence, we don't have in this kind of material, because for the sample I measure, we didn't have this evolution. We don't have this kind of properties of that material, because the evolution in terms of the frequency, we have this kind of evolution, for example, for some kind of vibrational mode, because you have some effect which can increase the difference between the vibrational mode. For example, if some vibrational modes vibrates more on the edge or more close to the center. For example, we have the butterfly mode, which are the first frequency that we measure, where we have you have a larger part. Probably I have a picture somewhere of vibration really close to the. Here, in picture 3.7, you can see three kind of vibrational mode, and you have the first one, which is a butterfly. The red part is where the sample vibrates more. Instead, for example, the second mode, the drum mode, is something that we cannot measure because you have a vibration exactly on the suspension point of the system. And the mixed mode, where you see that the edge vibrates less than, for example, the butterfly mode. This vibrational mode and frequency vibrational family can increase basically the frequency dependence of the mechanical loss through also the annealing step, the heat treatment step, and through the resonance frequency. In our case, what I got is basically a more or less flat mechanical loss through all the vibrational mode, apart yeah.
Okay.
Thank you very much.
Thank you.
The opposition will be continued by Dr. Matteo Tacca, researcher in gravitational wave detection instrumentation at NICEF.
Thank you very much. Dear candidate, I would like first to thank you for the nice job that you did. I should say that I learned a lot reading your manuscript. And I would like to continue the discussion about the last question asked by my colleague on figure 6.10, meaning that you are presenting results about different materials. And imagine for a moment that you will be the leader of this research. And which one will you push in the future and why?
Thanks you for your question. Yeah, first of all, we have to understand that the material investigator are for two different kind of detector. I did investigation anti-silica and anti-germania for the current detector at room temperature for the next upgrade of the current detector. Instead, for example, the amorphous silicon is something that we can use also for the current detector, but is the material for the next generation, like Einstein telescope. So, if Germania and in particular silica are really interesting. I will push on this amorphous material for the future, for the next upgrade, for the future investigation about the current detector. For example, I have a lot of money, for example, for the Einstein telescope and something like that. There's a research line about also the crystalline material. But the problem for the crystalline material is are too expensive, too difficult to create a larger sample for what we want to create.
Okay. Completely different topic is really about the experiment that you did. So you presented two very similar but also very different experimental setup, the one for the disk and the one for the rods. Could you explain a bit what were the challenges that you faced to go from, I guess, the well-known experimental setup that you use for the disk to this new experimental setup for the rods, and if you see that there's a room for improvement in both experiments?
Thank you for your question. You are right. They are similar because we have a vacuum tank and a GENS, but they are quite different because for the GENS, I explained during my talk how the GENS for the disk-shaped sample works. Instead, for the rods, we have a different setup because we have the problem that, for example, the vibration amplitude for the rods, because what we measure is something which is on the cross-section of the rod, not along the length of the rods. So in this case, we have really a small amplitude in a signal. For that reason, we implemented the system with the interferometric readout. So, and you can see here in the picture 6.3, no, 6.3, no. There's a complete an overview about the setup. Outside the vacuum tank, we have basically a Michelson interferometer. So this is with where one mirrors is the sample itself. The other mirrors is this voice coil, the figures 6.4 letter C, which can basically reproduce the other mirror. And we created this system to measure really small amplitude in vibration for the mechanical loss of the system. Obviously, always can be improved for the setup, and you have seen during my presentation, I started with really in office room, so with a lot of noise also from the environment. We have a wooden box, now we have an optics table for our setup, the vacuum tank which creates a lot of vibration for the measurement, because obviously you have also all the vibration of the system correlated to your setup. So An improvement is always possible, and we did during these years of my PhD. And for example, at the moment we have for the GENSA setup in Maastricht, we are quite confident on the measurement and reduction in terms of noise from the other source of noise. For the interferometer at Lyon University, we have something that we can improve, and we are in Maastricht they are trying to reproduce this system to measure the mechanical loss with all the device in best performance.
Okay. Do we have time for last question? Yeah. So, looking at the result that you presented here and there in the thesis, at some point I encountered the problem of the aging of the samples. So I have a couple of questions about that. Were you aware of it before starting the measurement or not? How did you discover that this was a real problem, and how did you try to solve it?
Yeah, I'm not aware before the measurement, because this is something during the year, during the months of my measurement. If you look at figure 4.1, at the beginning I had this substrate, fused silica substrate. I measured this one in 20 September, then I remeasure because I have some spare time in November 2021, then in March 2022, what's happened? The loss increase. So is an effect that we know for the sample, because we know the aging effect, we know how the sample, in particular the substrate, behaves due to this effect, and this is something that we can reduce. I explained before the aging, what is the main problem for the aging, and we know that with the annealing, the heat treatment temperature, we can reduce this effect.
Viola Spagnuolo, the time appointed for defending your thesis has now passed. The degree committee here present will now withdraw to discuss the quality of your thesis and your defense today. And therefore I request that you and your company await the results of our deliberation and our return in this room.
All right, please.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. side. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and not. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and not. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
Viola Spagnuolo. The degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Hilt is authorized to confer upon you this academic distinction in accordance with Dutch university custom, and I invite now your supervisor to take the floor.
All right, please.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by the law and in conformity with the decision of the committee here present, I hereby confer upon you, Viola Spagnuolo, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university.
Please, I now invite the supervisor and co-supervisor to give the laudatio.
Dear Viola, you were our first PhD student in our back then very new department, and this made it a rather big decision for us to decide who our first student would be. And what made us decide for you was that you seemed to be very determined to do this PhD, very enthusiastic, and also actually your slightly unusual CV seemed to speak for you and your determination in that, at that phase. I also just had the feeling that you would fit in very nicely with our group. I'm sure it was also a very big decision for you to decide to start a PhD far away from home in a new country. Soon after you started, we were all hit by very unexpected circumstances. Due to the pandemic, the country went into lockdown. There were several periods during which we couldn't go to the office or to the labs. We were encouraged to stay home. But this was all, even when the department was still very small, and it was hard to keep up communication. But we tried to do our best with online coffee and pub meetings. During all this time, you did an amazing job with setting up an experiment, first in an empty office, as you showed us before, with the wooden box, which I loved up to the end. And there were also fun times. I remember meeting you in the corridor, being desperate about the sample already ringing down for 10,000 seconds and not stopping, and other, just fun stories between us, like our first bottle of isopropanol back at a time where we were not allowed to have any solvents in our not equipped apartment, and the bottle which you always had to take home with you because we couldn't store it anywhere. So, and then, the worst of lockdown finished, and our group started, everything started getting back to normal, and our group started growing, and it grew from just the two of us to, being 7 of us. And now I would like to hand over to one of those 7.
So I will now say a few words in Italian so that your relative and your friends that are following us remotely can understand. Viola, ricorderò sempre la prima volta che mi hai mostrato i laboratori a Maastricht. Allora non era altro che un ufficio e la strumentazione era appoggiata sulla stessa scatola di legno con cui lo strumento è stato spedito. Tuttora scherzo su quella scatola e tuttora sono sbalordito di come tu sia stata in grado di ottenere dei risultati buoni, ottimi, nonostante le cose a disposizione erano semplici come una scatola di legno. Sei la mia prima studentessa che ho co-supervisionato ufficialmente e con cui ho avuto il piacere di lavorare a più tempo. Sono fortunato perché nonostante tu sia il primo studente, mi ha reso il lavoro molto facile. E questo è perché sei una persona che si impegna sempre e che non si tira mai indietro di fronte alle difficoltà. Ci siamo incontrati come colleghi, ora siamo amici e mi mancheranno le nostre chiacchierate al mattino seduto sulla sedina dello sconforto quando ci tiravamo sul morale a vicenda durante i periodi di stress. Ma sono felice che hai trovato un posto all'interno della collaborazione, quindi per adesso possiamo tenere gli addii da parte e lasciare spazio alle congratulazioni meritate per questo risultato ottenuto. I will now leave the words again to Jessica.
So I hope you said what we agreed upon. Yeah, so for me, it was a great pleasure to see how we grew from just the two of us into a group which set up a very nice lab, did great science, but even more importantly, had a lot of fun together at conferences, occasional dinner, and always laughed a lot during our weekly meetings. And I hope you enjoyed these times as much as I did. You were a very important part for getting this little codings group in our materials lab started, and we couldn't have had a better first student for our group. Congratulations on finishing your PhD, and all the best for your future. Thanks.
Dear Dr. Spagnuolo, also on behalf of Maastricht University, I would like to congratulate you with the degree you have acquired. A doctorate's value, of course, lies not in what you've done to get it, but what you do with it. And I think everybody here is very confident that you will do great things with it. A doctorate is, after all, forever. So, congratulations. We will now, well, first make a little picture at the stairs with all the people in dresses, and then we will head off to the Refter for the reception, to which you are all very warmly invited. Thank you very much.
No, volevo portare. Così devi portare tu.